Hi everyone. In this video I'll be talking about 4.1 and 4.3. So we're going to start with related rates and then talk about extreme values. So for related rates, as we're seeing all too clearly with the latest events, the world is a very connected place. So there's a lot of related quantities. Right, the more I work from home, the more my weight goes up. The more time goes on, the older I get. Just think about all the related quantities in your life. There's a lot. So to talk about a specific example here, here's example 1. So we have a pretty simple situation happening. We have a spherical balloon being filled with air at a constant rate. So that rate, 2 cubic centimeters per second, is fixed. That is how fast this pump is expelling air into this balloon. So it says how fast is the radius increasing when the radius is 3 centimeters. So naturally, as this balloon fills up, the radius, the point from the center of the balloon to the surface of the balloon, will naturally increase as the volume goes up, right? As more air comes in, that will lead to a largening balloon, so that radius will naturally increase. So as the rate of the air takes effect, that will relate to the rate of the radius increasing. So just to read it again, it says a spherical balloon is being filled with air at a constant rate of 2 cubic centimeters per second. How fast is the radius increasing when the radius is 3 centimeters? So what I'll be doing to kind of give us some structure is I'll be following these 5 steps. So this is on the next page, page 56. So I'll kind of be going through these 5 steps with respect to this balloon. So in step 1, we want to basically figure out the variables that are involved. So for that step 1 over here, I'll write R. I'm going to represent the radius. And then I will let V represent the volume of the balloon. In step 2 of that 5-step process, it says basically to state in terms of the variables the information that is given and the rate to be determined. So something that was given was the rate at which air is coming into the balloon. That is the volume rate. So the change in the volume with respect to the change in time, that's the change in volume of the balloon. So that rate was given as this 2 cubic centimeters per second. So this was a given. We were also given the fact that we care about the rate of change of the radius when the radius is specifically 3 centimeters. We are looking for in this case, it says how fast is the radius increasing. So we are looking for, in terms of variables, dr dt. We want to know what this thing is. Okay, so that's kind of what we know and what we don't know and what we're given. On to part 3 of that 5-step process. So step 3 basically says to figure out an equation that relates the variables. So now that you've defined the variables that are involved or important. You now want to find a governing kind of overarching equation that relates those two variables of interest. So it's kind of a natural equation in this one. We're concerned with a sphere's volume and radius. So the equation that governs this situation would be the volume equation of a sphere. So V equals 4/3 pi r cubed. This is kind of the general equation that relates the variables that we care about from step 1. So step 4 is using the chain rule. And really implicit differentiation. We're going to differentiate both sides with respect to t. So I'm not differentiating with respect to v or with respect to r. We are differentiating v and r both with respect to t because v is actually a function of t. It's changing with time. R is also a function of t because it is also changing with time. So both v and r are both implicit functions of t. So we are going to, in step 4, differentiate with respect to t. All right. So this differential operator can be applied directly to v, so I'll just write dv dt. And then I'm going to pass the differential operator past these constants, so I'll just say 4/3 pi and then d dt of this r cubed, which still needs to be done. So that will lead to, again, I just still have dv dt equals 4/3 pi, and now taking the derivative of r cubed with respect to t, I get 3r squared, but then the chain rule, implicit differentiation basically, I take dr dt, because I know in the back of my mind that r is itself a function of t. Okay, so simplifying this derivative, we can write dv dt equals 4 pi r squared dr dt. So this is step 4, and then step 5 says substitute all known values into the equation from step 4, then solve for the unknown rate of change. Just as we were saying in step 2, we are looking for dr dt. So this is the thing I'm looking for. I know r is 3. I know dv dt is this 2. So I can substitute. So 2, that's dv dt, equals 4 pi times r squared, which is 3. So I'll have 3 squared, and then times dr dt. Okay. So now going ahead and squaring, writing this more simply, we have 2 equals 3 squared is 9, so 9 times 4, I have 36 pi times dr dt, and then dividing both sides by 36 pi. So I have 2 over 36 pi equals dr dt, and in other words, I can say 1 over 18 pi. and that would be in units of centimeters per second. Since it's dr dt, that's the change of a radius, in other words distance, over the change of time, in other words seconds. So this would be dr dt in simplified form. In other words, the rate of change of the radius with respect to time, exactly at the moment when the radius is 3 centimeters. Okay, so on to page 56. It's another related rate problem, but the context is quite different from the one we just did, but same 5 steps can be applied. All right, so let's read it. That's kind of step 0. So an airplane is flying overhead at a constant elevation of 4,000 feet. There's a picture over here. So it says, a man is viewing the plane from a position of 3,000 feet from the base of a radio tower. The airplane is flying horizontally away from the man. If the plane is flying at the rate of 600 feet per second, at what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? All right, so it looks like variables have already been kind of assigned for us. I have s and x. Here's this constant 4,000. Here's this plane going that way at 600 feet per second. So with respect to number 1, this number 1 here, I want to describe the variables, or assign variables. So I'll let s represent the distance from man to plane. In other words, this same variable right here, s. And then I'll have x represent the distance from man to tower. In other words, this x here. And I'll let dx dt, so the change in the horizontal distance with respect to time, I'll let that represent the plane's speed. And then finally, I'll call ds dt, the change in this distance here with respect to time, the rate at which s is changing. In other words, the distance or the rate of change of the distance that we care about, right? Because the last part of the question said, at what rate is the distance between the man and the plane increasing? So really, we're going to be looking for ds dt. So in part 2 of that kind of 5-step process here, so part 2, state in terms of the variables the information that is given and the rate to be determined. So something that we know is that x is 3,000 feet. We know that this vertical distance is fixed at 4,000 feet. So you could now, with the Pythagorean Theorem, solve for s. So s is not directly given, but you can figure it out. It's implied. So s would be that hypotenuse of that right triangle here. So I'll have 3,000 squared plus 4,000 squared. That would all equal s squared So the square root of that should equal s. So that would be a 3,000, 4,000, 5,000 triangle. So this would be 5,000 feet. So s was actually implied to be 5,000. We are given that x is 3,000. Right, that's given here. Right here. And we are also given dx dt, in other words, the plane speed, right? It's going this way. So dx dt is happening at 600 feet per second. And that was given here. Okay, we are looking for ds dt, as I mentioned before, so I'll just say ds dt equals what? This is the thing we're looking for. So part 3, find an equation relating the variables that we care about in this situation. So basically we have a right triangle, and what we're concerned about is the rate of change of one of the sides of that right triangle. So just like I used the Pythagorean theorem here, that really is the governing equation. So the governing equation would be this x squared plus 4,000 squared equals s squared. Right, where x is this base of the triangle, 4,000 is this other leg of the triangle, and s is this hypotenuse, this longest side of the right triangle. So that's 3. Step 4, use the chain rule, and also I'm saying implicit differentiation, because again, we're differentiating not with respect to x or s, but we're differentiating with respect to t. So in step 4, I'll differentiate with respect to t, both sides. And then I'll pass this differential operator to both terms. So I'll have 2x, right, power rule, but then dx dt, since x is a function of time, we are given this 4,000 is a constant. So the height is not changing with respect to time, so that'll just be 0. So the derivative of 4,000 squared with respect to time is 0. So nothing more there. And then derivative of s squared would be 2s ds dt. Okay, that's the derivative of our governing equation. The thing that we're looking for is ds dt, as I mentioned over here. So what I'll do is simplify, or isolate rather, ds dt. So I can divide both sides by 2s. I'll get x dx dt over s. Those 2's will cancel, and that'll be ds dt. And now step 5 is to plug in what we know. So I know that x is 3,000 at this moment that we care about. So 3,000 times dx dt, which we know to be 600, and then divide by s, which we figured out over here is 5,000. So plugging all that in, you'll find 360, and that would be in feet per second. This would be ds dt. All right. This follow-up question, it says, what is the speed of the plane if the distance between the person and the plane is increasing at the rate of 300 feet per second? So right when we got here, basically here, let me write that down again. We had x times dx dt over s equals ds dt. So in that situation, we didn't know ds dt, and we did know the other things. In this situation, what they're giving us here, that is the distance between the person and the plane. So that is actually ds dt this time. And what we're being asked to find is dx dt this time, the speed of the plane. So if I reorganize, you'll find that dx dt would be equal to s ds dt over x. Just algebraically rearrange that. And now we know everything over here, so I can plug in. So s was still this 5,000. Now ds dt is assumed to be 300. And then I'm dividing that by x in this case, which is still assumed to be this 3,000. Doing all that, and you'll find dx dt, in other words, the plane speed in this hypothetical, would be 500 feet per second. All right, so I'm going to leave example 3 on page 57 open. Of course, I'll do the problem after the video, and then I'll post the solutions of this problem and the rest of the ones I don't do next to the video. Okay, so on to 4.3. We're talking about maxima and minima now. So in this section, we'll be interested in finding the locations at which a function is maxima or minimum. For example, we will have a cost function and be looking for the dimensions of a product that will minimize the cost. So perhaps you're making a can, you're making millions of these cans, let's imagine. So any savings you can make on one can will perhaps multiply largely and save the company a lot of money. So you would want to make maybe a 10-liter can for the cheapest amount. So you could do the job of carrying whatever 10 liters of liquid it is, but for the cheapest amount possible. So calculus will allow us to figure out dimensions of cans or whatever the vessel is or whatever the situation is that will most ideally fit into what we want. So for instance, you might find what is the maximum acceleration of the space shuttle during some trip, or what is the radius of the contracted windpipe that expels the most air during a cough. Just some random examples of what we would mean by maxima and minima. At what angle should blood vessels branch so as to maximize the energy expended by the heart in pumping blood? Here are the formal definitions of local maxima and minima values. We'll be talking more about absolute. I think the best thing to do is probably draw a quick picture. I'll let you guys dig into these definitions. Let me draw a quick picture for us, and I think it'll help clarify what is meant by absolute maxima and local maxima. So imagine we just had some graph, and maybe it's doing this. Let's see. So let's just have it stop like right there. And actually, let's extend this part down here. Okay, so here's our hypothetical graph of this function f. And let's say we wanted to know the local min and max and the absolute min and max. So what is meant by absolute, maybe I'll start with absolute first. So by absolute min or max on an interval is just literally what is the lowest number achieved and what is the greatest number achieved. Just what is the smallest output that is achieved and what is the largest output that is achieved. That's it for absolute. So just looking at the graph, it looks like that this would be the highest value that I achieve. And it looks like over here would be the lowest value that I achieve. So let's just imagine that this was a 5 and that I'm getting a 10 here. So this corresponds to f of 10, let's just imagine. And let's say that this is -2 over here and that this corresponds to sorry, I don't mean f of 10, I mean f of 5 is 10. Sorry, correct that. And here, this is f of -2, and let's just imagine that's achieving -1 here. This is -1. Let's also imagine that this is happening right here at 3, and then it corresponds to f of 3 equals 1. And then I'll imagine that this is 1.5 and that this value corresponds to f of 1.5 equals 7. So let's just put some numbers to this. So the absolute min, so I would have an absolute min of -1 at -2. So I would say f of -2 equals -1, and that output is really the min value. I would have an absolute max. In this case right here, this is the highest the function gets on this interval. I'm just going from -2 to 5 in this case. So I'd have f of 5, but the max itself would be the number 10. It's always the output that is the actual min or max. Okay, and then for local, to be a local, you need that your derivative is 0 there. So in other words, this cannot be a local. Right, the slope of the tangent line there is not 0. This over here would also not be a local. This can be a local, right? And that does look like a local because the derivative would be 0 there. This tangent line would be horizontal, in other words. Here's also another local. That would be a local min. And this would be a local max. So maybe I'll just slide this over here. Hopefully you could see this over here. So for local min, I would have this only one right here. So I'd have f of 3, but then the min itself would be 1, the output value. And then I would have local max. I have a couple of them. Actually, I have one here. So I'll have a local max there of 7, and then I'll have another local max here of 10. So I'll have f of 1.5 equals 7, right? The 7 right here. And then I also have f of 5 equals 10. And these outputs are actually the local min. So we had absolute min, absolute max, we had local min, local max. Hopefully you can see the difference. Absolutes do not need to be derivative 0. So to be an absolute, you do not need to have that your derivative is 0 there. Sometimes it'll be 0 there, and it's fine if it does, but it doesn't need to be. For locals, you do need to have that the derivative is 0 there. So I'm going to go on and look at page 58. So page 58, I want to read this definition of critical number. So a critical number of a function f is a number c in the domain of f such that either the derivative is 0 at c, or the derivative at c does not exist. So what we'll see is that we'll take the derivative of a given function, and then we'll set the numerator equal to 0, and that'll spit out critical number c. And then we'll set, if there is a denominator, we'll set that denominator equal to 0 also, and that'll spit out critical number c, because the derivative won't exist when its denominator is 0, right? You'll be dividing by 0 there. So, for example 1, it says find the critical numbers. That's all we're doing here. So f prime of t, I need the derivative, since critical numbers come from setting the derivative equal to 0, and also where the derivative doesn't exist, I definitely need the derivative to figure this out. So I'll have 3t squared, power rule, plus 12t minus 15. I do not have a denominator that's going to produce any critical numbers in this case. So really, for this case, I'm just considering this. There is really no spot where this polynomial is undefined, right? This polynomial is defined everywhere, meaning no critical numbers will be pulled from this possibility. We'll just have this possibility for this example. So set this equal to 0 and solve. Factor out a 3. It looks like that'll make things a little bit easier. Divide by 3. So in other words, we're looking for when 0 equals t squared plus 4t minus 5. This looks like it factors as t plus 5, t minus 1. So in other words, we're getting critical numbers when t plus 5 equals 0, or when t minus 1 equals 0. So the critical numbers would be t equals negative 5, right, solving this equation, and t equals 1 for this function. We'll see why the critical numbers are critical in a second. Basically, we're going to need to be able to figure out critical numbers to be able to figure out min or max. Okay, so example 2, I'll do this one also. So different function, but still we want critical numbers. So what that means is we're going to take a derivative and then consider either of these. Critical numbers come from this, or they come from this. So f prime is needed. This was for the above. So f prime of x, it looks like the quotient rule is needed here. So low d high minus high d low. So low d high minus high d low over the low one squared So here's our derivative. I'll simplify. Now we're getting into this material, as I mentioned, where we want to simplify often these numerators. Excuse me, and then set them equal to 0. And this is when we're doing this, to find these critical numbers. So that's why I was having you guys kind of getting used to factoring and thinking of setting these things equal to 0 with that foresight. So I'll just do some simplifying here. So x squared minus x plus 1, and then some quick algebra there. If I factor, I'll get negative 2x squared, and then it'll actually be plus 3x minus 1 after you distribute the negative, and then over x squared minus x plus 1, all squared still. So in other words, we have that f prime of x is, combining like terms, I have negative x squared. I have plus 2x, and then that's it. And then on bottom I have still this denominator, x squared minus x plus 1, all squared. So for this function, there is going to be perhaps a location or locations for which the derivative does not exist, right? So what we're going to do is set this equal to 0 and set this equal to 0. Setting this equal to 0 will make f prime equal to 0. Setting this equal to 0 will search for locations for which the denominator is 0, meaning the derivative doesn't exist there. Both of which would be critical numbers. So we're wondering where negative x squared plus 2x equals 0, or we're wondering where x squared minus x plus 1 all squared equals 0. Solutions to these two equations will produce critical numbers. So here I can factor. So negative x, and then leaving behind an x minus 2 equals 0. Over here I can maybe take the square root, or just realize that really we are wondering where x squared minus x plus 1 equals 0. So over here I'm getting critical numbers of x equals 0 and x equals 2. Over here, thinking about the quadratic formula, I'd have 1 plus and minus the square root of 1 minus 4 times 1 over 2 times 1. These are not real, right? If you look at the discriminant there, that would be negative 3, the square root of negative 3. So you're not getting real solutions from this part. In other words, this thing never achieves 0. In other words, there's no x such that the derivative is undefined. In other words, the derivative is defined everywhere. So although it was possible that we were going to get critical numbers from this piece this time, we didn't again. And we only got critical numbers from f prime equals 0. So we got these two critical numbers here. Okay, so on to page 59. I'm going to leave example 3 open. I will post a solution to example 3, however. Let's go on to example 4. This is our first one where we're not just looking for critical numbers, but we're being asked to find the absolute maximum and absolute minimum values of f on this given interval. So we have 0 to 5, this quadratic. We're looking for the largest and lowest, right? Just absolutes. That's all we're asked for, is absolute, absolute. We're not asked for local. if you type this thing into Desmos, I totally encourage you guys to be kind of checking Desmos as you're working on these. It just gives a nice visual aid, because a lot of the stuff is getting to be visual. If you do that, you'll see that this graph, just to sketch it, looks something like this from 0 to 5. If this is 5, this is 0, of course. So this is basically our graph. So it looks like I'm expecting an absolute max here, and then I'm expecting an absolute min there. So just to put a picture to it, that's what we're looking at here. To find that with calculus, so f prime of x, so start with the derivative. So we have 4 minus 2x. Set this equal to 0. This is, we're not going to have that the derivative is undefined anywhere, right? The derivative is just this linear polynomial. So you can plug any number into this and you're never going to divide by 0. So we are not getting critical numbers from that second option. We're just getting critical numbers from f prime of x set to 0. Solving this, we'll have 2x equals 4. Divide by 2, we get x equals 2 as a critical number. So this must be happening here at 2. If you wanted to figure out algebraically whether this is a min or a max, well, one way to know is that this is a downward opening parabola, so it must be a max. Or you could use a sign chart. So you could place this critical number on the sign chart and then do a test. So what I'll do is I'll test over here maybe at 3. So this is a test. So I'm going to find f prime of 3. So 4 minus 2 times 3. This is negative 2, which is less than 0. So over here, it's a negatively sloped line, tangent line. And that's this negative slope, or that negative slope, or that negative slope. That's why this is a negative number, because I just tested on the right of our critical number, and I'm getting a negative value, which is really an indicator of slope. If I test on the left, maybe I test over here at 1. So this is a test. So f prime of 1 is 4 minus 2 times 1. That is 2, which is greater than 0. So on the left, I have these positives, that positive or that positive. Excuse me. Which is an indicator that this is a max, because we have positive slope on the left and a negative slope on the right and a 0 slope right in the middle at 2. So we have a max at 2. I know it's going to be the absolute max based on the picture, but you wouldn't really know that based on the picture yet. So let's see, I need to check. I need to find f of 2. So you're always going to find the function evaluated at your critical numbers. And then you also need to check the endpoints. So I need to find f of 0 and f of 5 to see what they're doing, because maybe they beat this value. So let's see, f of 2 is 12 plus 4 times 2 minus 2 times 2, right? I'm plugging 2 into the original function. And out of that, we get what? We get a 16. Now f of 0, plug in a 0 to the original function, and obviously we get a 12. And now finding f of 5, plug a 5 into the original function, we get 12 plus 4 times 5 minus 5 squared, and we're getting a 7 out of that. So I'm looking now at these numbers, and there's basically a race to the top and the bottom, right? So this looks like the winner for the max, and this looks like the winner for the min. So we have an absolute max of f of 2, but the max itself is the number 16. And then we have an absolute min happening at f of 5, but the min itself is that number 7. And that's all this problem wanted. Find the absolute max and the absolute min. So on to page 60. All right, I'm skipping example 5. You'll see the key for that. Example 6. So it says find the absolute max, the absolute min. We're tasked with the same goal here. So for sure we need the derivative. What we're going to do, we're going to take the derivative, figure out where that derivative is 0. We're going to evaluate the function there and then at the endpoints. So f prime of x equals, so this derivative formula for ln, we have 1 over the argument, and then times the chain rule d dx of that inner function. So in other words, we have 1 over x squared plus x plus 1 times 2x plus 1. So we have this as our derivative. We have 2x plus 1 over x squared plus x plus 1. So now we want to set the numerator equal to 0. Look for critical numbers there. Set the denominator equal to 0. Look for critical numbers there. So 2x plus 1 equals 0. This means that x equals -1/2. That'd be a critical number that's going to go on our sign chart. And then x, so it would be or, x squared plus x plus 1 equals 0. So that's setting this now equal to 0. Doing that, we get x equals opposite of b plus and minus the square root of b squared minus 4 times a times c, this quadratic formula, over 2a. But again, this is not real because of this negative discriminant there. So we are only getting this critical number. So what I'm going to do is now place that critical number on a sign chart to see what kind of value it is. Is it a min or a max? So -1/2, place it there, and then I'm going to test around it. So I'll test over here. I'll use 0 as a test, and then I'll test over here. Maybe I'll use -1 as a test. So plugging in a 0, so go to the derivative now. I'm plugging in this 0 to here. This is a sign chart for the derivative, not for the original function, right? This is a sign chart for f prime. So testing at 0, f prime of 0, if you plug in a 0 here, we'll get 1 over 1. It looks like 1 to me, which is positive. I know that I get exactly 0 at -1/2. That's why it's a critical number. Testing over here, f prime of -1, plugging in a -1 here, what do we get? it looks like a negative number. I don't even really care about the value, it's just the sign. So that means I have negative slope on the left, positive on the right. This critical number leads to some kind of min, in other words. So this perhaps is the absolute min. We don't know until we check the endpoints, right? Because maybe the function dips below. Maybe it goes below this local min to create a different absolute min. So we're going to evaluate f of negative 1/2, f of negative 1, and f of 1, just like we did previously. Right, so there's kind of a race now. So f of negative 1/2, so that would be ln of negative 1/2 squared plus negative 1/2 plus 1, and that would be ln of 3/4 in exact form, but just so we know, so we can compare, that would be about negative 0.29. Then we also had f of negative 1, so f of negative 1 equals ln, right? I'm going back to the original function, right? We're looking at outputs now, and we want to see, okay, which output is the lowest, in other words, the absolute min, and which output is the greatest, in other words, the absolute max. So that's why we're looking at outputs now. So negative 1 squared plus negative 1 plus 1. So 1 minus 1 is 0 plus 1. This is ln of 1, which is 0. And then f of 1. This is ln of 3, in other words, about 1.1. And now what we're doing is comparing this output, and this output. The lowest will be the absolute min, the greatest will be the absolute max. So absolute min here, right? So we'll have an absolute min f of negative 1/2 equals, and I'll write it in exact form, right? I'm not going to write this because the min is exactly ln of 3/4. The problem didn't say to round. Then I have an absolute max. So this is that min, by the way. Then I have an absolute max. It looks like of this value. So that was f of 1, which equals ln of 3. This would be that absolute max. Okay. There's that one. One more, and then you'll be able to go back after the video and look at solutions. So this one, I'm going to again try to pull up the computer in a second and show you how to use it in Desmos to solve this. So it says on May 7th, 1992, this space shuttle Endeavour was launched on mission STS-49, the purpose of which was to install a new perigee kick motor in an Intelsat communication satellite. The table gives the velocity data for the shuttle between liftoff and the jettisoning of the solid rocket boosters. Okay, so it says part 1, use a graphing calculator. In other words, for us, or for me at least, I'm going to use Desmos. to find the cubic polynomial that best models the velocity of the shuttle for the time interval t in 0 to 125. Then graph this polynomial. Part 2, find a model for the acceleration of the shuttle and use it to estimate the maximum and minimum values of the acceleration during the first 125 seconds. All right, so for part 1, we're looking for v of t, a cubic polynomial that models the velocity as a function of time. So what I'm going to do is go to Desmos. I'm going to type in this data into a table, and then I'm going to use that function inside of Desmos to do a regression and find a best fit cubic polynomial for this data. So I'm going to move the camera so you can see the computer. Okay, so desmos.com. Over here you can type in this plus, and then go table. And then what I'll type in there is all of this data here. So that'll be my time. And then in the right column, I'll type in all the velocities. So I'll have 0, 10, 15, 15, 20, 32, 59, 62, and 125. And then here I'll have all those velocities that are given. So 0, naturally, it's sitting on the ground at time 0. 185 after 10 seconds, and that's feet per second. So 319 after 15 seconds, and so on. 447, 742, 1325, 45. Okay, so now what you can do if you want to see the data, because it wasn't really popping up very well, I see this point, and that's about it. Maybe I'll make this more visible. So over here, I can type, or I can click on this little magnifying glass, and then it'll just nicely appear. Then in the next cell, I'm going to do the regression. So y1, so I'm calling on this variable. So y1, and then I go shift, and then, I don't know what to call that, but I'm going shift, and then I'm hitting that button right here. So shift, and then this, you want that little wavy. So that means y1 regressed against, and then since it's a cubic, I'll have a constant, and then x1 cubed. That's not a great fit. You can see the line doesn't really, describe the data very well. So we're going to add in other terms. So I'll go b, x1 squared, a quadratic term. You can see the line's kind of starting to improve. And I'll go c, x1, and then a linear term, and then finally a constant, and this would be our polynomial. So you can see down here on the bottom left, these are those constant values. So I'm going to write down this polynomial where a is the coefficient of the the cubic term, b is the coefficient on the quadratic term, and so on. And then I'll hold it up in front of the camera in a second. So I have v of t is 0.0014637, and that's a t cubed term, minus 0.115534. In other words, b, and that's a t squared term, plus 24.9817, that's a linear t term, and then minus 21.2687. So I've written down this polynomial here. And we're looking at the graph. So that is the graph. I'll just sketch it. So here's my quick sketch of that graph. So it said, use a graphing calculator to find the cubic polynomial. That's v of t there, and then graph. So that's fine. Okay, so part 2 says find the model for the acceleration and then use it to estimate the max and min of that acceleration. So if this is v of t, then if I differentiate, right, if I find v prime, that's now a formula for the acceleration. So for part 2, let me maybe bring you back down here. Sorry about this. All right, so for part 2, what I'm going to do is basically find v prime. That'll be the acceleration function. So writing that down, I'll use the power rule. So I'll multiply it down by 3. So I'll get 0.00438,411, and now that's a t squared term. That's a 4, by the way. And then also power rule here. So I'll multiply down by 2. I'll get negative 0.231068. That's a t now. And then I'll have plus 24.9817. So this would be the model for the acceleration that they were talking about. Here's our model for the velocity, by the way. So to continue with the problem, what we now need to do is figure out a way of figuring out the min and max of the acceleration. So if you're wanting to find min and max of a function, what have we been doing? So if we were given a function and we wanted to find its min and max, we would take its derivative and then set that derivative equal to 0, do a sign chart perhaps, test the endpoints. So what we now need to do to figure out the min and max of the acceleration function is to differentiate the acceleration function and then set it equal to 0, figure out the value there, that critical number, and then test the endpoints, right? So here's the acceleration function. To figure out the min and max of it, I need to take the derivative of that function. So v double prime of t would be, again, multiplying down by 2, this power rule, I'm getting 0.00876,822t, that linear term. And then differentiating here, I just get that coefficient, so negative 0.231068. So now setting this to 0, looking for that critical number. So v double prime of t set to 0. solving this. So solving that for t, so if you solve that for t, what you'll find is t equals 26.35289,717. So this is would be a critical number of this acceleration function. So what we're going to do is find v prime of it. I'll call it maybe t1. So I'll find v prime of t1, and then I'll find v prime of 0, in other words, the endpoints, just like we were doing before, and v prime of 125, the endpoints of our interval from the data. Right? This is our given interval in this case, essentially. So v prime of t1, this number that I didn't want to write again. So let's go ahead and type that in. This might take a second. So plugging that in, we have, so I'm plugging that in here, by the way. Sorry, here. So it'll be 0.00438,411 evaluated at t1, and then squaring, right? This number that I just don't want to write a bunch of times. And then I'll have minus 0.231068 times t1. And then we'll have plus 24.9817. So let me do that. It's going to take just a quick second. So it looks like I'm getting, I'll just say about 19.565. And that would be feet per second squared. And then for v prime of 0, plugging that in is pretty easy. I'm just getting this constant. So 24.9817, and that would be feet per second squared. And then v prime of 125, I need to figure that out. So 0.00438,411 times 8. Sorry, I made a calculator error. Okay, I'm trying that again. So what I'm doing is plugging 125 into this function, looking for the acceleration there at that endpoint. Okay, so it looks like I'm getting about, well, I'll just say it's about 64.600, and that's feet per second squared. So the max would be this one, this last one that we just found. So about 64.600 feet per second squared. And the min would be this value here. So about 19.565 feet per second squared. So those are the max and min values for acceleration during the first 125 seconds of this space shuttle's journey. So I'll go back and do the problems I didn't do on the video. I'll post those alongside the video, of course, as a key. What you'll also find there are problems. So the group work problems that I would have done in class, you'll find those next to this video as well. It's not your group work anymore, but it's just more practice problems, and then I'll post the solutions to those alongside the video as well. Please do comment and engage with the video. I'm counting your comments as your group work. All right, I will see you guys soon. Well, you'll be hearing from me soon, and I hope to see you in office hours soon. All right, bye-bye.